Fessenden today. He joined my lab about 6 years ago, and he was the first biology graduate student to join my lab, and not only that, but he's a cancer biology graduate student. And I think what happened was I invited Val Weaver to give a talk, and he fell in love with her work, and then he comes to me and said, you know, do you know about this whole field of like mechanical regulation of cancer metastasis? And I was the next best thing to Val Weaver here. But he braved joining my lab. As some of you know, we have a lot of physicists in the lab, and he learned to start asking questions. I think you can now ask questions to people doing all sorts of variety of in vitro and cell work in our lab, which is, I think, hopefully you've gained some insight and knowledge from that. But importantly, Tim taught me a bunch, right? So when we've been working on single cell migration and adhesion of single cells, and Tim taught me everything there is about, obviously, cancer that he knows, and then also about epithelial cells in general. And he developed all the assays for 3D imaging and 3D cell culture that you'll see in this talk. None of that was established in my lab. So he did that all himself by talking to lots of people, both here at the University of Chicago and other places. So that is a really hard thing to do. And I think Tim deserves a lot of credit for taking the initiative and really establishing his own direction of research in my lab. And I'm really proud of you for doing that. And so he'll tell you today about his thesis work over the past 6 years.
Thank you for the kind introduction. So I'm gonna it's a huge pleasure and an honor to be here today to present to you. I thought about this day for so long. It's kind of amazing. It's like scary, mind-blowing. Without any further ado, this is an overview of what I'm going to talk about today. So after a little bit of background, I'm going to tell you about a type of tissue shape change that I've been working on for a while now, called branching morphogenesis. And I'm going to tell you about that with one particular model that I've used, and then I'm going to draw some parallels to a mouse tumor invasion assay. And then after making some brief conclusions on that, I'm going to dive in back to the cell line that I've used to really understand some of the mechanistic, deeper mechanisms that are going on during this tissue shape change. Okay, so with that, as I said, I'm really concerned with how tissues acquire and change their shape. And so this happens obviously in many different scenarios, but certainly during development. So what I'm showing you here is a mouse kidney. Over a span of several days, as you can tell, it grows in size and becomes much more complex into this branch structure. But on the other hand, as the other schematic is showing you the progression and invasion of breast carcinoma. So that's kind of another sort of tissue shape change where you have a normal duct that fills in and eventually those cells begin invading into their surroundings. Hallmark of kind of my work and the work in the Gardell lab is that it's really hard to understand biological systems by looking at sort of these static pictures. So you might think of it like trying to understand a tennis match, or even trying to compare between 4 different tennis matches. If you look at a series of photos, it might be really hard to figure out like who's winning or how the match is going or even how the match works. But as also is the case in biology, we can actually gain a lot of intuition by looking at just a little bit of live data of watching things happen in real time. So indeed that bears out when we take the example of development. So this is a movie made by the Ewald lab at Hopkins, and all this is showing you is the developing mammary epithelium in a mouse. And the different cell labels don't mean anything, they're just randomly labeled cells to highlight how cells rearrange and change shape in order to accomplish this elongation. On the other hand, the Ewald lab has also studied cancer invasion. And in that case, they've shown how, using live imaging, how different lineages, in this case these are marked by red and green, actually have different roles during invasion, where the cells that are marked in green are leaders. And that's actually, they showed it was actually very important for breast cancer metastasis. So these are very complex tissue shape changes, and I wanted to reduce this problem to understand it better. And so I use MDCK cells. This is a cell line that's been well established and for like decades now, actually. And if you put them in the right context, they form these clonal model tissues. So I'm going to show you a Z-stack. So this is scanning through the full volume of one of these tissues. So in cyan is actin, which is a cell structural protein that effectively marks the cell membranes. And then in magenta are the nuclei of the cells. So you can see how they're arranged very nicely, and they form this hollow center. But the really cool thing about these cells is that if you give them one cue, this growth factor, they undertake this really complex collective shape change that results in the formation of these interconnected tubules from the initial spheres. So how that works experimentally is I plate the cells in matrigel. They form these these model tissues. I isolate those structures intact from the matrigel, and I replate them into collagen gels. And that's where all the action happens. So this won't happen unless it's in a collagen gel. So everything that you're going to see today is actually from those last two steps. So everything's in collagen that you're seeing. So how does this look in my hands? Here's an example. This is a stain for actin, that same structural protein that I'll get into. This is the initial state, and then after 48 hours in this growth factor HGF, you can see the elongation of these multicellular branch structures. So that's called branching morphogenesis. And it really allows us to ask fundamental questions on a very basic level using an immortalized cell line, right? That can explores how a contained mass of cells that's in one place and with very little interaction with the surroundings can become this extended, branched, invading structure, right? In the case of development or of cancer invasion. And so to begin to answer this question of how this works, we can pose some really simple questions, like what would cells have to do to go from the one state to the other? And you can imagine, very simply, cells have to change shape, they have to be malleable, they have to form adhesion to their surroundings, and they remain adhered to their neighbor over the course of this process. Unfortunately, these are phenomena of single cells that have been studied for decades in the field of cell motility. So before I go any further, I'm just going to give a brief overview of how cell motility works and the proteins that are responsible. So if we take a cell, this is an endothelial cell from Claire Waterman's lab at NIH. So this cell is moving through a collagen matrix, and you can appreciate that it's definitely changing shape. And it's forming adhesions to its surroundings, and it's doing so actually in a specific cycle that cell biologists have identified is pretty well conserved. So that looks like this. First, cells form a protrusion from the leading edge in the direction of migration. They form new adhesive structures within that protrusion, and then they retract the rear of the cell. And this works in a cycle to effectively propel the cell forward in one direction. So it's these three different activities are constantly cycling to affect cell motility. And these actually have been very well characterized in terms of like their molecular determinants. So if we take one cell moving in this direction, this schematic is showing you in red the actin cytoskeleton. And this is separated into a leading edge, which is a site of protrusion, of advance of the cell's edge. And that's formed by this branched network of actin. And then back from that is the cell body, which contains these stress fibers, which are formed by linear bundles of actin. So this branch structure at the front, it's formed by, it's made by a complex called ERP23. So it polymerizes this actin. Meanwhile, in the cell body, stress fibers are formed by a family of protein called formins. And the cell body is also the site of a lot of the activity of myosin, and myosin is the motor protein that provides contractility, which is required to move the cell rear and integrate the cell, basically, front to rear. And then in between, of course, are focal adhesions, and these are these adhesive sites that I mentioned. So these interact with both ARC2/3 mediated networks as well as Foreman mediated networks. So with this in mind, I was really fortunate in that branching morphogenesis undertaken by MDCK cells actually has been shown to rely exquisitely on exactly these proteins, right, that mediate exactly those same actin structures that I just mentioned. So HGF directly activates two upstream regulators, which result in activation of ARC2/3, Foreman proteins, as well as mycin. So you can just, if you just keep in mind, there are two very different actin organizations that result at the same time from HGF activation. And the only other thing to keep in mind is that in contrast to the actin that I showed you in that schematic of the cell, as you can tell, the actin in three-dimensional cell culture, it's just mostly peripheral. So you mostly see what you're seeing really is the cell membranes, the cell boundaries. But we'll get into that a little bit later. Okay, so with this in hand, I'm going to ask the fundamental question that I've been concerned with are how all the cytoskeletal dynamics that I just went over briefly, how are those changed in individual cells in order to mediate this transition? So first I'm going to go over how that works in MDCK cells as far as I found, and then also in mouse tumor explants. So we've used an inhibitor to ARC2/3 and Foreman's to ask, first of all, if you just have a control like at rest tissue, what happens when you inhibit Foreman's or ARC2/3. And there wasn't a whole lot of change in the case of Foreman inhibition. ARC2/3, the cells look a little bit weird, as you can maybe tell by the cell shapes, which is obviously actin staying there. Then I did the same assay, except I stimulated them with HGF to induce branching morphogenesis. And I was very surprised, we were all actually very surprised, that inhibition of Foreman's completely blocked branching morphogenesis, whereas inhibition of ARC2/3 did not, even though it was clear that the cells were a little bit weird looking and there was some funky business going on. Relative to controls, we can see this really beautiful branching morphogenesis. This was not really prevented in the ARC2/3 inhibition context. So I just quantified that by counting how many of these little extended protrusive structures I would see per acinus. And it was really remarkable how much inhibiting Foreman's just blocked all of that activity. So this was our first clue as to how this process was controlled in 3D. And then I moved to a mouse tumor model. This was with the help both of Matt Perez, who's now in Amy Zhao's lab, as well as a former student of Prajita, who's in Kami Cloud's lab. So we use a mouse genetic model for mammary or breast cancer in mice. These develop mammary carcinomas. And what we did was we took out a mammary gland that had tumors, chopped up the tumors, and just plopped them directly into a collagen gel, and then allowed them to invade into the collagen gel with no specific signal. And what we found was actually really similar to what I just showed you with the MDCK cells. So inhibiting ARC2/3 after 24 hours did not prevent the cells from extending invasive fronts into the gel, whereas inhibiting Foreman's did. And that was quantified the same way as before. So this really validated, at least in these a very different model, that it seemed like these same proteins were really important for invasion. But to clarify how this looks, I just talked about how important live cell imaging is. If you take these pieces of tumor, imaging live shows how, in the control case, they really rapidly form these multicellular fronts that extend out into the collagen gel from the initial site. Whereas when Foreman's are inhibited with this inhibitor here, there's no formation of even these fronts, although the cells kind of seem to move around. So this suggested that indeed these two, at least from these two models, these tissue shape changes as I define them really may require similar cytoskeletal regulators, even though they're in very different contexts and they're undertaking these shape changes sort of from different stimuli. So now I'm going to move back to the MDCK model because that's a cell line where we can manipulate it genetically. And so the first thing that we did was ask, okay, there are 15 members of the forming family in mammals. Which ones is important? So we initially chose 3 forming family members. Di1 is like very well known. It participates in all the canonical structures that hormones are known to create. FOD is a little bit atypical mostly because it has a different upstream regulator and it's localized to the cell front. And Di2 we expect to be fairly similar to Di1. So with the help of Yvonne Beckham in the lab, we made stable knockdown lines in which each of these was reduced at least by 50%. And then we asked, okay, so we have these cell lines, can they form the same tissue structures in the first place? Can they even form an acinus? And indeed they could, although in the case of Di2 knockdown, which you see all the way over on the right, the tissue looked a little bit aberrant. But otherwise, at least as assessed by Acton, these different cell lines seem to be fairly similar to the control. And then I asked the same question as before, obviously. So if we add HGF and we ask them to undergo branching morphogenesis, what happens? And encouragingly, knockdown of Di1 and knockdown of FOD1 prevented branching morphogenesis to similar degrees, whereas the Di2 knockdown still looked really odd compared to the control, but still was able to undertake branching morphogenesis, or invasion, I guess, in this case. So this was encouraging, but it didn't necessarily prove that something funky wasn't going on between these two, right? So they look normal by the Acton stain that I'm showing you here relative to the control, but we wanted to be sure that they weren't somehow messed up in some other way. So the way to address this, what has been really well established, certainly for the cell line, is that these cells are formed very, very specific interactions at the inner surface, the apical surface, and the outer surface, the basal surface. And they segregate a lot of their proteins to one side or the other, and so this gives rise to 3D polarity. And that actually has a lot to do with how the original tissue functions. So it's something that's really conserved across tissues and in cell culture. So the way that we assessed this by immunofluorescence was to look for lateral junctions. So that's E-coherent would be there. On the basal side, you have laminins, which forms the basal membranes that cells make. And then at the luminal face, there's a specific protein called protocolixin that these cells make there. So just to show what that looks like, if we look through the middle of an acinus, the staining for E-coherent, protocolixin, and laminin looks like this, with each of these proteins at the right place. And then we were very encouraged to see that the short hairpin for Di1 looked roughly similar in its localization to the control, as well as the short hairpin to FOD1. So it seemed like these model tissues look normal and indeed have at least these core polarity proteins in the right place. So now that we're assured of that, we wanted to dissect why would it be that Dia1 specifically would really be required for this process. And we focus on Dia1 because FOD, which is the other protein that I showed the knockdown of, that's kind of a non-canonical protein, and much more was known about Dia1. So first thing I wanted to ask was, is there just a generic motility defect? Can the cells just not move at all without Dia1? So to answer that question, I actually turned to 2D culture, where these cells can move quite readily. So if you take MDCK cells and you stimulate them with HGF in 2D, they undergo this rapid dissolution of these little groups that they form, and really rapid cell motility in 2D. So I wanted to ask, okay, this is a control case. Can the Dia1 knockdown cell line also do this? And indeed, they could. So this was something of a surprise. We quantify or I track the cells, and there wasn't really a big difference in this average speed or the sort of the directionality, measured directionality. So this seemed to not be show us anything meaningful about branching morphogenesis. So then we said, okay, perhaps these cells might be rearranging within the tissue. So to better understand how cells might move around relative to each other in these 3D tissues, I made cell lines in which they expressed a nuclear marker. So this is H2B and cherry. And what you're seeing is the projection of the lower third of the tissue in one flat plane, so you can watch any rearrangements happen live. And I simulated them with HGF, and the name is done. And indeed, there was really remarkable cell rearrangements and kind of this rotation that I saw over and over again, which is really cool, very kind of surprising. And then I asked, okay, so how about the diagonal knockdown cell lines? And surprisingly, those could rearrange just fine. So this is all under the stimulus of HGF, but before there's any large-scale invasion happening. And just like before, I quantified cell motility, didn't see a really huge difference in the speed or the persistence of these cells. So together, we can kind of put those two pieces of data together and say, okay, if you're in one plane at least, maybe within the 3D epithelium or on a flat cover slip, your motility is not really going to be different if you don't have HGF. So that wasn't really answering our question about what was going on with branching morphogenesis. So to get a better grasp then on what was going on during branching morphogenesis, I just imaged these SNI in bright field to watch actually the initial steps of protrusion and to see if anything was going on there. So in the control case, this is how it looks. So you can kind of appreciate how there is this rearrangement going on. But at the same time, there's little protrusions that come out and they kind of wiggle around and they retract, but then some of them kind of hang on and stabilize, and those are the ones that appear to mediate eventual collective invasion. And so to get a more quantitative grasp on this, I calculated the lifetime of each protrusion, how long it stayed there, and then I plotted that against this length. And when I compared this to the SH dia1, so the cells that were knocked down for dia1, I could tell actually, you can tell by eye that there's just, there are still protrusions, but none of them seem to stabilize. And that was actually quantifiable. So it might be a little hard to see, but basically there's a shared population here of the shorter-lived ones that don't grow very long. But there are the few in the control case that do live very long and grow to larger lengths. Those are really lacking for the dia1 knockdown. So this seemed like it was actually telling us something important about how branching morphogenesis is proceeding in the system. And what we concluded was that there's a shared population of these small, unstable initial protrusions between these two, but that there's some defect in their stability in the case of the dia1 knockdown. And we had a lot of ideas. I had a lot of ideas. I banged my head around this for a very long time, and Margaret was really persistent, fortunately, in encouraging me to think about what could be going on with these different protrusion dynamics that I was seeing. But I put this together, so what we've seen so far is that there's some motility that is independent of dia1. It doesn't matter if these cells have dia1 or not, they can still undergo these rearrangements. But then there's other motility, right, that's really contributing to the invasion that I'm trying to understand, and that seems to be exquisitely dependent on dia1. And so what Margaret pushed me to do, which was very successful, was to really think about this in terms of the adhesion to the collagen matrix that these cells are in. So I looked closer at the collagen matrix, and I did that by imaging, by fluorescently labeling the collagen fibrils that are around cells. And as you can appreciate, it didn't take me long to realize that indeed the cells were deforming the collagen around them. So you can see two examples there as they start to protrude from the acinus. Meanwhile, in the case of the knockdown, it seemed like there was maybe less, right? There's fewer protrusions, first of all, and then there's like hardly any movement of the collagen fibrils. So I set out to dissect this difference that seemed apparent using markers for the cytoskeleton. So I made cell lines that had the control shRNA or knockdown for dia-1 protein that also expressed a marker for actin and a marker for myosin. So this is the result of that. So this is after just 4 hours in HGF, so fairly early on. And the thing that I was able to quantify was the movement of really adhesion to and movement of individual collagen fibrils. So this movie loops to show you 2 different views. And in both views, if you just follow the arrowhead, it shows you the collagen fibril that this one cell encounters, adheres to, and moves. And meanwhile, the other fibrils around it aren't moved really at all. So if you look down here, there's the one fibril. So this is the actin, that's the myosin, and the down here is the collagen. So I was able to image this enough times to get a good number on it for basically how often this happens at this early stage. And the important thing about this early stage is I can compare it to the knockdown, because at this stage they look sort of similar. They both kind of squirm around. And what I noticed was if you look at one collagen fibril in one cell, you don't really see the fibril being moved, even though the cell is right up against it. So the cell kind of just warms along, and this collagen fibril isn't really moved at all as the cell kind of moves along by. So I counted these events, and I could tell indeed that there was a defect in the ability to deform individual collagen fibrils. And this seemed to really jive with this idea that there was a defect in the ability of cells to adhere if they don't have this dia-1 protein. So I wanted to verify this, that indeed there was, that we could see the cytoskeletal activity as cells were deforming collagen. And so if I looked later on, so this is 24 hours after HGF, you can see an actin and myosin coalescing at the cell front as the collagen fibrils are deformed. So in this case, because it's long enough out, the cell is invading, right? It's collectively, it has all its neighbors within, it's moving out into the collagen. But I couldn't compare this to the dia-1 knockdown because they don't even form these, right? But what it hinted was maybe there's something going on at the cytoskeleton that's telling us something important about adhesion to the collagen, right? I was, for one, was really surprised to see myosin way up here at the front of the cell where this collagen deformation is going on. So what we wanted to ask was whether myosin was actually showing us where adhesions were forming. And so to get into this question, I have to give you a little bit of background on focal adhesions. So I showed you this before, but one important thing about the adhesions specifically here is that focal adhesions are formed at the cell front, and they actually undergo this canonical maturation process. This has been very well described for cells migrating in 2D. And during this process, they grow in size. An individual focal adhesion plaque will grow in size, and it'll also change in composition. So this has been the object of a lot of study for cell biology. And so there's a lot of literature out there to say, okay, what proteins go where and when. And this work built actually on the work of a previous lab member, Patrick, who showed some really, really fine detail on how this process works. And in this work they defined, so this is the RP3 network here at the cell edge, and they defined this area, this zone, as a zone where nascent adhesions are formed, but not yet stable. And then they have to be stabilized as they enter the cell body, which is back here and is more full of myosin and dominated by formin proteins like dia-1. And what the crucial thing that he showed was that dia-1 is actually required for this maturation process. It was already known that myosin was required. It was less well understood how dia-1 participated. So this allows us to really define these zones. So this is where R23 is really dominating, and there's less myosin. And then here in the cell, for the cell body, dominated by dia-1 and myosin networks. And we can mark these. This is work that's been well established by now. This one protein, pexillin, is present in all these focal adhesion states whereas specific residues that many proteins have that are phosphorylated tyrosines are really only present in the mature focal adhesions. So with this kind of framework, we then ask, okay, are we seeing immature focal adhesions? Are we seeing mature focal adhesions? What are we seeing? And especially, where is myosin? Because that was kind of a really curious finding that I had. And indeed, so in control cases, if you look at the very end of the cell front, the actin shows you this enrichment at the cell front, and the myosin is there. And there's paxillin, so this is a protein that marks all focal adhesions, immature or mature. And then, if we look at phosphotyrosine, we also see that it's enriched where myosin is as well. So this suggested that indeed myosin was showing us sites of focal adhesion assembly and maturation. Not that we were, I'm not going to claim that we were watching it happen live, but at least we were able to mark it. And that these canonical focal adhesion proteins that have been very well established for 2D migration are indeed participating in the elongation of this multicellular branch. But again, unfortunately, I can't compare these control cases with the Dia-1 knockdown because it doesn't form these structures. So again, I went back to an earlier time point to say, is there a difference that we can mark across these two populations? And indeed, there was. So this is the basal surface. So this is just like kind of grazing the bottom edge of one acinus. And you can see myosin collected in these dense structures along the surface, along with phosphotyrosine. And then in the case of the knockdown, the myosin distribution is really different, and the phosphotyrosine, it's not that it's not there, but it's definitely distributed differently relative to the control. So this seemed to agree with a focal adhesion defect, especially mature focal adhesions that phosphotyrosine would be marking. And I counted up all these dots, and indeed there was a significant difference across these two populations. And the really cool thing was I was able to verify the same data that Patrick had shown, but with MDCK cells. So this is the exact same cell assay that I showed the video of before of cell scattering in 2D on cover slips. And this is a more specific marker for focal adhesion maturation. This is phospho-Fab. And so we know that these cells can scatter. That we've seen, no problem. But they still have this hallmark of defective focal adhesion maturation. So we concluded that focal adhesion maturation is not really needed, actually, for this kind of motility in 2D, but it seems to be explicitly required for branching morphogenesis in 3D, which was a really nice claim, I guess, to get to make, because focal adhesion maturation is such a well-defined process, which has been less well understood in 3D. So putting these together, this is our initial model, sort of, for how branching morphogenesis is initiated. So you have an actin-rich protrusion that's formed by one cell. That protrusion defines collagen fibrils. The initial adhesion causes an increase of actin polymerization and myosin recruitment to that site. And crucially, that requires Dia-1 to make linear actin structures that support focal adhesion maturation, in agreement with the work shown by my previous lab, Patrick. So we suspected that there should be some hallmark of Dia-1 in the actual organization of actin in these structures, and I haven't shown you any data to that effect. So indeed, I went and looked. And if you just look at the surface, so the basal most surface, you can see, I don't know how well this projects, but you can see that there are, in the middle of cells, there are little bundles that kind of emanate from the center of cells, many different cells. And then in the case of the Dia-1 knockdown, the actin organization is completely different, it's kind of just diffuse. And this is before any addition of HGF, so this is just homeostatic sort of control conditions. And then, if it's true that this bundled actin architecture is supporting, focal adhesion formation, and we think that we're marking focal adhesion with myosin. If you look for that hallmark, so 4 hours after HGF, where we can compare these two, you look at myosin, you can see this dense accumulation that's coincident with actin, with these little filaments coming off of it. And that's completely different in the case of the control, or sorry, the knockdown. Oh, you have this weak little spot of myosin, but there's not really much else with the actin going on with it. So this seems to corroborate this model that indeed you need bundles of actin formed by dia-1 and possibly other formins in order to make the correct adhesion structure that mediates invasion. So we can put these together in this model where what we think is happening is there's maybe a switch that cells can undertake in response to HGF, where some adhesions don't require dia-1. We see this in 2D, we see this in 3D, and cells can maybe rearrange within the tissue via these adhesions. But then other adhesions, so what we're calling mature adhesions, do require dia-1, and those are the ones that mediate invasion. And this should be the case, well, we expect it to be the case for the tumor, the mouse tumors that I showed you, and it's certainly the case for the MDCK cell line that I showed you. So we think that this might be the evidence of a switch, sort of a tissue level regulatory mechanism to control what kind of invasion you're doing, at least through a fibrillar network, such as collagen. But this actually leaves some unsatisfying contradictions. Namely, I showed you that there's a lot of rearrangement within the tissue, within these structures, at the same time that there's formation of stable adhesions to the collagen gel. And we can see hallmarks of that if you look at a single cell. So this is one cell, and it's formed this little puncta, this dense spot of actin and myosin that's adhered to this collagen fibril. And even as the cell moves, it stays stuck on that one spot, whereas in the case of the dia-1 knockdown, the same kind of spot can form, but it just moves kind of with the cell. It's not stably adhered. So this leads to kind of a little question that I haven't fully been able to investigate, but it's really like, is there a competition then between these modes of motility? Do cells compete with each other to form stable adhesions that are immobile relative to the gel? And there is some evidence for both, I guess. I've seen in some cases this one cell reaching out, and it's reaching out, it's protruding, forming adhesions to the collagen gel, but meanwhile its neighbors are moving right along. So there seems to be some maybe friction or some competition there. But then on the other hand, I was really curious to see, or really interested to see, this case where it looks like as one cell is moving along the collagen gel, you can see yellow, it's forming these adhesions that are marked in the myosin channel magenta, as well as the cyan, which is life act. And then as it leaves those, the next cell behind it has less life act, so you can kind of differentiate it, but it has myosin marker, and it forms new puncta in the same spot, so these new little myosin-rich adhesions forming in the exact same sites. And that suggests that there's some degree of cooperativity, maybe, that I'm going to do some on these adhesive sites, and then you're going to clone along after me, and you're going to grab onto the same sites. So this kind of brings into a whole different dimension of how do cells interact with each other, and how do they move relative to each other, all within one continuous tissue, which is something that's been really hard to study. But MDCK cells make a lot of cool tools possible. So for instance, as I showed you, you can look at nuclei and watch cells rearrange, but you can also mark individual cells. So I did this with just a simple virus that expresses GFP. So you can look at one cell, and you can look at how it's moving relative to all the other cells around it, and you can also monitor the whole tissue in bright field, which kind of leads to whole different ideas of how cell shape is regulated in this dynamically rearranging tissue, and how the motion of one cell maybe has to fight against its neighbors, but then goes along with its neighbors. And it really just brings up all of this crosstalk kind of between the collective behavior and then the individual cell behavior. So those are just tidbits. Finally, this video is to demonstrate that the imaging parameters that you use really affect the conclusions that you made. So if your camera speed is matched up to the helicopter's rotor speed, it just kind of floats away. And so what this is motivating is actually thinking more carefully. If we image just a little bit differently with, say, higher resolution or higher frame rate, we can learn a lot more and we can redefine the same structures. And so I was fortunate enough to use lattice light sheet microscopy to image myosin. This is myosin across an entire acinus, so you're not really resolving individual cells, but this is the whole tissue. And you can see how it's organized into these dense puncta, which I kind of alluded to this earlier. In the control case, they form these dense puncta, whereas this is the knockdown acinus. It's localized very differently. So these are stills of live movies, just to show you how much more you can see kind of with different imaging modalities. This was done with lattice light sheet microscopy that allowed me to infer a lot of not easily quantifiable, but like it allowed me to infer a lot of new data, new understanding about these. And what the myosin data showed, this is the myosin here, is that those dense puncta that I was seeing were forming these really dynamic structures that were assembling and disappearing and moving, while the diol knockdown formed these really wimpy, crappy ones, and there was just a lot of on-off. And when I went back and I looked at the conventional imaging that I do in Margaret's lab with the confocal, you can sometimes make out these little spots that merge of the myosin and the actin. So there's a lot of important inference you can gain, if not quantitative data from different imaging techniques. And then one other tidbit that I learned from the lattice light sheet imaging was in the imaging cells, here in red, and the collagen is in white. And movies like this helped me really appreciate how complex the deformations were in the collagen. So you can see this one cell is kind of moving along this way, and then it's kind of stuck to this one spot in the collagen and yanks a whole bunch of that collagen along with it. And in the conventional confocal fluorescence microscopy, I mean, I would see this, but it would be a little bit less rich, a little bit less detail. So you can see quite a bit. Finally, so I'm just gonna end by saying, hopefully you're convinced that cells do assemble these really interesting dynamic structures as they're carrying out this dramatic shape change. But I think that we might think about these, this is definitely Margaret affecting me, we might think about these more productively as materials and as a material property of this tissue, which could be helpful to think about how structure and function kind of go together as you scale up from the subcellular to multicellular scales, and how subcellular material properties can still really exert really strong effects on the multicellular behaviors. Which gets back to what I was saying before about how we think about different scales and the importance of the basic material that the cells are working with to carry out these shape changes. So with that, I'm going to thank the lab. There's a ton of people to thank. All this work is the result of many people who've helped me and supported me along the way in different ways. Former postdoc Patrick Oakes, who has his own lab, former postdoc Mike Morrell, who has his own lab, and Fred Katz, who started working with NBCK cells, he also has his own lab. They were super helpful, amazing postdocs when I first joined. Yumina was a grad student, she's now over at Stanford and UCSF. Matt Perez, who helped me a lot with imaging, came to Cloud's lab, who helped with the mouse work. And Andy Ewald, who showed his work, and he's just been a really nice, unofficial, off-site kind of mentor. He's been always really willing to respond to emails and have long discussions with me. I learned a lot of what I learned actually about 3D cell culture in Val Weaver's lab. I visited her lab for a couple of weeks, and that visit really accelerated my progress with the 3D cell culture. And then the lattice sheet imaging was done at the Genelia Research Campus. So more thank yous. I have to thank Margaret. So when I looked up our first emails, and I found that I thought that extraordinarily cool. Wow, this is extraordinarily cool. And it's just amazing because I had no idea what I was talking about. Yeah, it was pure speculation. And I want to get my hands dirty, and we did that, so that was good. And some of Margaret's favorite email techniques. And then the lab, we've had a lot of fun. It's a really, really great lab. I feel super lucky to have been with such an amazing group of people who, everyone's so friendly. People just, are relaxed and helpful. There's not crazy drama. We make liquid nitrogen ice cream. Things are really, honestly, really easy. This is Patrick, Nina, and me together. And then some really good friends. So Josh is here. Tim is here. There's another Tim. And then just friends. I have just been really fortunate to have a ton of friends that I've moved to Chicago since I moved here. Friends who are from the Bay Area, who are still in the Bay Area, or now other places. It's been an amazing journey. And finally, I have to thank my family. These are my three sisters. This is Rachel, Rebecca, and Leah. This is my mom, Judith. My mom died before I graduated undergrad, and I miss her a lot. She's an amazing person, and she never got to be here in a physical space with me over the years. So I miss her a lot. This is my dad and me. He's a huge fan of the science that I do, and I can talk to him about experiments, and he gets it, and he will ask the right questions and everything. And then this is all of us at Rachel's wedding. This is my godmother Karen, who's here. And this was an amazing, amazing day for all of us. And so I have to thank Karen for making the trip out. She's family too. So with that, thank you guys.